He is a researcher in the Space Sciences division here at Ames, was instrumental in the LCROSS mission, the science team on the LCROSS mission. And Tony is going to be talking about Resource Prospector, a lunar volatiles prospecting and ISRU demonstration mission. So, Tony.
There you go. I can get the company up here. Thank you for having me. It's good to be here, and to follow Paul's talk is perfect. I couldn't think of a better introduction than Paul's talk, so we'll jump right into this. Next slide. Should I control from here?
Let's see, how do
press the arrow at the bottom there?
I know. Just one like that.
this
arrow.
one, yeah.
Got it. Okay.
Oops.
Oops.
Oh,
Now you've
Sorry.
done it.
I know.
Okay, now try it.
There you go. Okay. Not a Mac guy, sorry. So as Paul pointed out, there's water in a variety of concentrations and forms that we think we are seeing on the moon now. It's a completely different paradigm than what we had just 10, 15 years ago. It was anticipated by many prior, but we really have the evidence now to confirm that there's just a zoo, if you will, of water on the moon, which is really fantastic. As Paul also pointed out, and what I'm going to reiterate is there's a whole lot we don't still know, and that's really important that we take the next step, knowing what we know now, and trying to devise the plans to take it one step further, both in terms of science exploration, but also from a human exploration standpoint. And that's what I'm talking about today. The resource prospecting mission tries to take it to the next level, if you will, for resource utilization and human exploration. So what we do know is there is water, but as Paul pointed out, we really don't know a lot about where it is and even the form of it. LCROSS showed there was water ice. That's important. We also have the surface observations from M-cubed and others that show there's probably adsorbed water there, or at least hydroxyl of some form, but we need to know more really if we want to understand the resource potential and how to effectively get at it, mine it, utilize it. So what we really need to understand is the distribution of water at scales that we don't have right now. If we resolve the water concentrations that LCROSS saw with the neutron data in the same area, what you have to do to reconcile those two measurements is assume that it's patchy. That if the several percent concentrations that LCROSS saw are accurate, correct, and in the top meter, which is where the neutron spectrometers sense, then you need to assume that it's buried under a certain amount of desiccated layer, 10, 20 centimeters, and patchy to some extent, maybe in the 20 to 40% concentrations, lateral heterogeneity. So that's pretty important if that's the case. We need to understand, and there's a lot of modeling that has demonstrated this, has looked at this as well. Dana Hurley's done some of this, that has shown that you need to, or just cratering, gardening and impact cratering redistributions in the top meter will create length scales of mixing that are on the orders of tens to hundreds of meters. So that, in my mind, is the next scale that we really need to try to understand the presence of volatiles in general on the moon. And that's really what Resource Prospector is all about. So the Resource Prospector is a prospecting mission and an ISRU mission. Its first goal is to really prospect, to verify the existence and the presence of the various volatiles we've seen remotely and through some excavation techniques, I'll put it that way, but really go down there in a much more controlled fashion and map these things out at scales of tens to hundreds of meters, up to a kilometer or more if we can. So what we're really trying to understand is those distributions, both laterally and vertically, of the volatiles. That's first and foremost. Then second is to get at those volatiles. That's part of the prospecting itself, is actually excavating and sampling and processing some of those volatiles, primarily water if it's there, but also then demonstrating that you can use that water, store it, manufacture with it, if you will, and produce something with it. And that's the ISRU part. And that's what Resource Prospector is going to do. It's first going to prospect, and I'll tell you the tools we're going to use to do that. But then it's also going to sample, analyze the volatiles in the soil, and also do a hydrogen reduction experiment using the oven system where we actually bake the material to generate water and create a water drop itself. So basically showing that, hey, you can breathe. Someone put it to me this way, I like it. You can breathe lunar rocks. That's pretty impressive. So right now, the Resource Prospector is in a pre-phase A study. We have a mission concept review scheduled for this September. It's right around the corner. We're starting to make slides, so it's very real and to us right now. It is slated for a launch in May 2018, and it will to the South Pole of the Moon. We actually designed for either pole and with contingency landing sites. As a phase A, it's really just a study. We need to show in the concept review that the mission concept will close, that it's a viable concept and can go forward then towards a system requirements review approximately 1 year later. Right now, it's categorized as a Class D Category 3 mission. For those of you who know what that means, it is right now currently a NASA and a Canadian Space Agency collaboration. There are other international partners who we're talking with who are very much interested in this, and we're very interested in making this an international effort. That is a story that is still being written. As a Class D mission and a Category 3 mission, it is not a large flagship type mission. It is relatively inexpensive in the terms of lunar surface, or planetary, I should say, surface exploration. So we're keeping it to areas that are solar illuminated, and I have a slide on this here in a second. It doesn't have any kind of nuclear power or anything like that that allows it to go into shadow regions for very long periods of time. We have level 1 requirements that have been signed off by headquarters. They are very and intentionally vague. That's a good thing for a Class D mission. I list them here. Really, the first thing is to land in the polar region. That's something we haven't done. That's a good thing to demonstrate. So a lot of Resource Prospectors really demonstrate new technologies, not only for the moon, but beyond the moon for Mars, asteroids, and other small bodies. But then once we land, to actually be capable of obtaining new knowledge at the scales I've just described about lunar volatiles. We then, at the project office, write level 2 requirements below those that flesh it all out. And this gives us, the project, a lot of latitude to actually address the problems in a way that is consistent with the Class D and Category 3 requirements. So here's some of those L2 requirements, quickly paraphrased. We are organized in a minimum, full, and stretch goal success in terms of the way we write our requirements. The minimum is really land and make some measurements in 2 places separated by at least 100 meters, and subsurface or surface measurements. And that's the minimum. We do that. We can be quite happy that we've successfully demonstrated a lander, rover, measurement techniques at the poles. But of course, we build towards the full success, and that's what's listed here. Is we really actually drive at least 1 kilometer. That's not odometer. That's point to point. And we make many measurements, subsurface and surface, and so on. And then there's a variety of stretch goals where we say, as the capabilities are afforded to us, or timeline affords to us, we try to do these things. So we organize our planning this way as well. So where to go? As I mentioned, we're keeping this solar panel, and that's important from a cost perspective and actually just a technical approach as well. And a lot of work's been done to look at these regions of overlap where you have what I call temporary sunlight. It's just sunlight for a week or so. And in these areas of temporary sunlight, just below the surface, 10, 20 centimeters, the temperatures are cryogenic. The average lunar surface temperature of those depths are well below the stability point for water ice. So there is a potential of having hydrogen-bound volatiles in these regions. We need to, of course, have traversable terrain. You have to have also, an important point, direct Earth communications. We want to be able to talk directly to Earth, not require an orbital asset if at all possible. A lot of study has gone into this. There are lots of sites that are, both high in hydrogen, have these attributes, And so both at the North and the South Pole. So we're very happy that with this, or we're confident we can find these kinds of sites and make them work. This is an example really quickly, I won't dwell on this, of the kind of analysis that has gone into it. For example, here's Cabeas Crater, and the L-Cross impact site was right there. All these red areas are areas where you have, if you will, stable water ice temperatures below about 10 or 20 centimeters. So there's a lot of area here. This shows the maximum days of sunlight. So for example, if you looked at a point here and a point here, you got a place where you certainly could have volatile stored just below the surface, 10, 20 centimeters, and you still have 5, 6, 7 days of sunlight. So it's kind of like Paul said, you can actually land in sunlight, delve into shadow, come back into sunlight. Thanks. Really quickly, this is what the notional payload looks like on a rover. This is a rover actually schematically using a field demo that I'll mention real quickly here in a second. It includes a drill system, which right now can both auger and core. It has a prospecting system that includes a near-infrared spectrometer that has both a camera system, a radiometer on it for measuring surface thermal radiances to know temperatures. It's got its own light source, so we can see in the dark with our near-infrared spectrometer. Kim Enico had a talk about this system, or a poster, I should say. You should go look for it. It gives a lot more detail there. It has a neutron spectrometer on it, of course. You gotta have that to really hunt down your hydrogen. And then once we get samples, we find a place with the prospecting instruments we want to do a core or an auger. If we core, we can bring that sample over to an oven we have and volatile analysis system called the oven and lava systems. And this includes a GC, a gas chromatograph mass spectrometer system to do analysis of any vapors that come off of the sample as we bake it. We can bake up to about 900 degrees centigrade to do the hydrogen reduction experiments as well. Again, the CSA is collaborating with NASA on the rover and the drill system. The rest is NASA provided. I'll be quick on this because I'm running short on time. This is really the functions of how it all comes together. We get there. We launched direct insertion right now. We land, and then we quickly start prospecting and looking for volatiles. We identify areas where we want to map them out in detail. We do that. We take samples, we process them, and then we demonstrate we can actually do something with the water. We either generate through hydrogen reduction or we actually just bake off from the soil itself. We've done a lot of notional traversing for this concept review coming up. This is using a tool developed by the Intelligence Robotic Group here, names called XGDs. This is one particular site. The red indicates permanently shadowed areas. Our landing site's down here, and it shows how we are driving along, jumping into each of these PSRs, jumping back out, and we're playing this with all the appropriate times, power usage data, and everything else to show how the whole mission comes together and fits in the box. The field demonstration was one step in doing that. We actually went out last summer, about this time last July, actually, a year ago, to show that you could actually do this with real hardware. We had a command center set up remotely. We drove actual hardware around looking for hydrogen-rich targets and other interesting things out in the field. And this shows our planned traverse and actual traverse, the red line. We were able to, in a few days' time, get over a kilometer traverse, find targets, do the science like we would be doing on the moon. So this was really just a demonstration of some of the techniques we would use in terms of the operations, which for a real-time lunar rover mission, you can imagine, are fairly unique compared to what we've ever done before. So finally, the summary slide, real quick. We're in this pre-phase A study. I said it's about half done. I wrote this slide for the Volatiles, virtual Volatiles workshop a couple months ago, so now it's 3/4 done. We've got the mission concept review, so with any luck, that goes well, and we move on to flight with the blessing of headquarters. That's it.
Yes, very good. I can actually shake someone's hand because you're not virtual. You're right here. Nice talk. So let's see. I am actually not.
No questions. That's good.
Yeah, not seeing. Oh,
Clive
wait,
Neal,
Clive Neal is typing. Okay, we'll give you a second here, Clive. How long can Resource Prospector survive in the permanently shadowed regions?
So the requirement that we put towards the engineers, and they've seemed to think they can close this, is 6 hours. And so that's mostly a battery size massing problem that you're probably aware of. So we are designing those traverses you saw so that we can go into PSR, do a variety of activities, either, for example, hunt first, drive back out, recharge our batteries, and then go back in. So 6 hours is the notional design life, but the idea is to attack a number of PSRs all along the way so we can go in and out, kind of like the way Paul described.
Yeah, great. Good luck with this.
Thank you.
2018 is not very long from now
No,
in the
no.
grand scheme of things. So, yeah, okay.